Okay, where we left off before was with fluorine, okay, where we wrote the electron configuration, 1s2, 2s2, 2p5, rather than drawing out the whole orbital diagram, which saved us some time. But it still takes a while for us to write out electron configurations without the lines and arrows, especially for really big atoms that could have a lot more electrons. Like, for instance, barium has a total of 56 electrons. I'm going to have to try and put them all in there. So there's got to be a couple more ways that we can make this easier on us, and there are. So the first thing we're going to do is show that the periodic table is set up in the way that it is for a good reason. So we kind of have seen that it's got an order to it from left to right and top to bottom, where we go in the order of atomic number, how many protons each atom has, and that kind of gives us the element. But we also have these weird kind of dips and valleys in the periodic table that wouldn't need to be there for the ordering of the atomic number. We could just go straight across from hydrogen to helium to lithium to beryllium, and then keep going until we decide that's where we stop, and then we move to another row, and then we keep going and move to another row, and so on and so on. So there is a reason for why we don't have that, why we have this kind of more complicated sort of like castle shape. Okay? The reason is that the periodic table is set up in what we call blocks. Okay, for elements ending in an s orbital or a p orbital or a d orbital or an f orbital in their electron configuration. Okay, meaning the last electrons we throw in are going to end up in one of those, and so their spot on the periodic table can tell us that. Okay, each row is going to indicate to us an energy level, which those were those numbers out front. Let me get, here we go, like the 1 of 1s or the 2 of 2s and 2p. Okay, those are our energy levels. And those tell us how far out the electrons are. Each column of the periodic table is going to indicate an electron in that orbital for that block. Okay, so that would be looking at like this 1s2 and this 2s2 and the 2p4. Each column indicates one of those electrons. So in the p block, we would have a column that accounts for this electron here, and then we'd have one that accounts for this electron here, and one that accounts for this electron here, this electron here, and then the other two that we're not showing in oxygen, up for a total of 6. Okay, so we're going to mark these on a periodic table so that we can kind of have this shortcut, so we can jump right to the end of an electron configuration. Kind of run over the end there, but that's okay. Just, oops. Just going to put my exclamation point back in over here. There we go. So let's switch over to the periodic table and see what we can do with it. All right, so let's use the periodic table to give us some shortcuts here. Okay, first off, I'm going to number the rows down the left side of the periodic table. 1, 2, 3, 4, 5, 6, 7. We also call the rows periods, which is why we call this the periodic table. We have repeating properties that have to do with when we restart a row. So those properties are periodic across the table. So there you go. Now these also go all the way across. Okay, so even though we got this kind of gap here, hydrogen and helium are both still in the first row, the first period. Lithium, beryllium, boron, carbon, all these guys are going to be in the second row, the second period, and on like that. Okay, so we have 7 rows on the periodic table. We also have 7 energy levels in the electron cloud of an atom. So these are actually going to be a good sign for what our energy level is going to be. So anything in the first row of the periodic table here across like this is going to be ending with an electron in the first energy level. Okay, something in the second row will end with something in the second energy level, and then the third energy level, and then the fourth, and the fifth, and the sixth, and the seventh. At this point, we don't know whether it's going to be an S or a P or a D or an F orbital, but we do know it's going to be in that energy level. To figure out whether it's going to be an S, a P, a D, or an F orbital, well, we've got to look at blocks of the periodic table. For instance, our first two columns of the periodic table, right here, oops, there, fix that a little bit. Okay, this is our S block. Oops. In other words, all these elements here are going to be ending with an electron configuration with an s orbital. So something like magnesium would end in the third energy level with an s orbital. So it's either going to be a 3s1 or a 3s2. So how do we figure out if it's an s1 or an s2? Well, I mean, we got two columns here. So how about this? This is going to be our S1 column, and this is going to be our S2 column. Right there. Okay, and then we just kind of play battleship with this. We kind of go across, we go up and down, and see what we land on for that element. So something like calcium would end in the fourth energy level. Okay, and it's in the s block, so it's getting in an s orbital, and specifically, it's landing in the second column of the s block, so it's going to be ending in an s2. So calcium is going to end in 4s2. Now, when I go to write out the electron configuration for calcium, or any element for that matter, I have to start and move through the same order in the same place. So I'm going to have to start with calcium. 1s2, 2s2, 2p6, and keep working my way up. And now I know that I'm going to end at 4s2. Okay? So all I have to do is follow those diagonal arrows, okay, until I land at 4s2, and then I can stop. I don't have to worry about counting electrons the whole way to make sure, I don't have too many or too few. Okay, as long as I end at the right point, then everything else before that should be correct, which can save us a lot of time for bigger atoms, not trying to count how many electrons we have total, how many we've kind of allocated in the electron cloud so far. Okay, so that's our S block. Let's look at our P block next. Okay, that's going to be over on the right side of the periodic table. And here, it's going to be kind of this box over on this side. Ooh, that was pretty bad. Let's try that one again. That's better. All right, now you might notice that I've kept something out of the P block. Actually, let me write this over here. You might notice I've left out helium from the P block. And that's because it kind of belongs over here for some reasons of its properties. It acts similarly to neon and argon and krypton in the way it bonds and stuff like that. Or in some cases, the way it doesn't bond. But in terms of electron configuration, helium actually kind of belongs in the S block. It only has 2 electrons, so its electron configuration is going to end in 1s2. So it's going to be right there, actually. Okay, so in terms of electron configuration, helium is kind of lost. It's kind of supposed to be over here. It's sort of an honorary member of the 18th column with neon, argon, krypton. These guys we call the noble gases. But really, in terms of electron configuration, he belongs over in the S block. All right. Now the p block over here uses the same kind of rows all the way across. So again, this is the second row. That means we're ending in the second energy level. Okay. Third row means third energy level. Fourth row means fourth energy level, and so on. So I'm going to copy these row numbers over here. Oops. And I'm going to kind of have to overlap some elements, but that's okay. 2, 3, 4, 5, 6, 7. Try not to obscure them if I can. Okay, so these are energy levels. So if something's going to end in a 2p something, or a 3p something, or a 4p something, or a 5p something, okay, we'll know by looking at this. All right, now just with the S block, let's see if I can move this a little bit. Just with the S block, the column should tell us which electron we're dealing with, which one we're ending with, okay, in here. So first column is going to be my P1 electron. Okay, second column is going to end in P2, third is going to end in P3, then P4, whoops, P4, then P5, and then down here with neon and everything, this is going to be P6. So neon, argon, krypton, xenon, radon, all that are going to be ending in P6. Note that helium is not one of them. Helium only has 2 electrons. They don't even get close to the 2p6 orbital. So not going to happen. So neon and below ends in P6. And again, we just play Battleship with this. We can say, okay, well, third energy level, it's in the 5th column of the P block, so chlorine would end in 3p5, okay? Or arsenic. The arsenic is in the 4th energy level, 4th row. It's in the 3rd column of the P block, so it's going to end in 4p3. Okay? So that's the P block. D block is next. Okay, we're going to do blue for this one. The D block is kind of this valley here, this dip of the periodic table. Comes around this way. Okay, now depending on which periodic table you're looking at, the D block can be easy or it can be a little confusing. And in this case, it's a little bit confusing. Okay, now I've kind of left this corner kind of obscured here for a reason, because these elements down here kind of are supposed to be up here in this spot. Okay, and I don't think this is the best, way to show it. So for the purpose of this video, we're going to simplify this and say that this is the D block here. Okay, and what's left down here is going to be the F block. But in reality, that's a little bit different. We actually end up with the D block kind of being like this. But these guys are part of the D block. Okay, now typically we don't do the electron configurations of these guys down here just because that's a lot of electrons, it's a lot of stuff to write, even if you have a shortcut like this. So, we tend to kind of avoid stuff. And stuff down lower on the periodic table also tends to get weird, where they start putting electrons. The diagonal pattern we use gets us pretty close, but it's not perfect. There are some odd things where the electrons don't always follow the order we expect them to. Okay, so truthfully, this is kind of more what our D block looks like, and this kind of part of the periodic table should be kind of crammed up in between here. So the actual periodic table is a lot longer, but we don't use these elements a whole lot unless we're doing stuff with nuclear chemistry, so we just kind of shove them out of the way. Okay, so this is our D block technically. Now to make things a little bit easier, I am not going to look at that like that. I'm just going to say this whole block here is our D block. All right, and this guy is going to be our F block down here. And if you get into advanced chemistry, then you can worry about, where exactly the D block and the F block end and things like that. So for now, we're just going to call this the D block here in the middle. All right, now just like with the other ones, the other blocks, the periodic table. Okay, if this is the D block, well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns in the D block. And I have the d orbitals that can hold a total of 10 electrons. 5 orbitals that can each hold 2. So these column headings are going to be my D1, my D2, my D3, my D4, my D5, my D6, my D7, my D8, my D9, and my D10. All right. Now, for our energy levels, we could try to keep going across and say, okay, well, this is the 4th energy level, so this would be like the 4D1, the 4D2, the 4D3. But we run into an issue here. If we do it that way, we don't have any electrons in the 3D orbitals, which are kind of important. They kind of need to be there. So the way this pattern is going, we're kind of missing out on the whole energy level of d orbitals, which is not good. So unfortunately, it's going to get a little more complicated since we need to have some 3D electrons. This is going to be the 3rd energy level across here for the D block. This is going to be the 4th energy level across for the D block. This will be the 5th, and this will be the 6th. Okay? Now to check yourself to make sure that that turns out right, we can also check this with the P block. Okay? Now the P block doesn't have anything in the 1st energy level, but we don't have p orbitals in the 1st energy level. If you go check that diagonal chart, the only thing that's in the 1st energy level is the 1s orbitals. Then we start the p orbitals in the 2nd energy level and go all the way to the 7th. D orbitals only show up in the 3rd through 6th energy level, which is why we've got this kind of allocated here. So our normal row numbers don't really work for the energy levels of the D block. They're kind of one behind. Okay, but we can still just kind of make our own row numbers for these guys and say, well, it's not the number all the way across, but we're just kind of changing this here. Okay, so that's kind of our correction for the electron configurations of the D block. So something like chromium here would end in 3D4, and we just add in all the electrons across the diagonal pattern until we got to 3D4 and then stop there. Something like rhodium would end in 4D7. All right, you can see that there. Something like platinum would end in 5D8, and so on. So that's our D block. Now again, if you go looking up electron configurations for some of these deeper elements, there's some wonky things that happen, and it's not always the electron configuration you expect. But we're not handling any of those kind of problems in this class, so do not worry about it. Okay, and this just leaves the F block. Our F block is going to be this section down here. And again, I'm making a simplification here, but we really don't touch the F block all that much. So you can kind of ignore and avoid those issues. F1, F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12, F13, and F14. All right. Now, if we go check that diagonal pattern, I actually have it down here. We only have F orbitals in the 4th and 5th energy levels here. So This makes it a little bit easier since it's already kind of separated. And my little island of misfit elements down here, this is going to be the 4th energy level going across from lanthanum across to ytterbium. And then this is going to be the 5th energy level going across from actinium to nobelium. Okay, so these are the blocks of the periodic table. Let me write an F block for this. All right. And we can use this to jump straight to the end of an electron configuration rather than trying to, count it all the way up until we run out of electrons. So with the way that the periodic table is set up, we should be able to look at its placement on the periodic table, what row it's in, we call it the period, and what column it's in to figure out where the electron configuration is going to end. We can't make it to the end of the electron configuration unless we fill in everything else before that. So if we can follow that diagonal chart and just kind of fill in everything up to that point, we should get the right electron configuration. So if we look at iron, iron is kind of in the middle section of the periodic table, so it's in the D block. All right, and you might want to check your own periodic table to make sure you can follow along with this. Okay, now iron is in the 4th row down, but in the D block, that is the 3rd energy level. All right, because otherwise we're missing the 3 Ds. So our iron should end in 3D something. And that is the, let's see, 1, 2, 3, 4, 5, 6. It's in the 6th column of the D block. So it should end in 3D6. All right. So I just have to write out everything that gets up to that point. So if I look at my diagonal chart here, that means I'm going to go through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and then I don't have enough to make the whole 3d10, so I just stop at 3d6. So let's write that out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 is where I end at. Okay, and I can go back and add those up and check and make sure that I've got the right number of electrons. Iron should have a total of 26 electrons. We've got 2 plus 2 is 4, plus another 6 is 10, plus another 2 is 12, plus another 6 is 18, plus another 2 is 20, plus another 6 is 26. So all the electrons are there and accounted for, and rather than totaling them up and having to kind of keep track as I write out the electron configuration, I can just jump right to the end. Now, even though that makes it easier, this is still a really long electron configuration, and this only has 26 electrons. When we get into some bigger stuff like osmium with 76 total electrons, that's going to be a huge pain. So here's what we can do to kind of shorten this up. The further we get into chemistry, the end of the electron configuration, where we have the electrons on the outside of the atom, turn out to be the most important ones. The ones on the inside, where we start with the 1s2, 2s2, 2p6 every time, those don't end up doing a whole lot for us because they're so close to the nucleus. They're very strongly attracted, so they don't really get anywhere close to the action. The stuff that gets close to the action is the farthest out. Okay, so if we can abbreviate the beginning of the electron configuration to cut out the middle kind of electrons, kind of before we get to the outer edge, we call those core electrons, we should be able to get to the important stuff. The way that we can do this is to look at the periodic table and see where we leave off kind of in the previous row. Since we're going order from left to right, we're not really going to miss anything if we just start a new row and say, well, this is what happens after I get done with the previous row. So it's kind of like leaving a bookmark or a checkpoint there. Okay, so where we leave off is column 18. Okay, that's the kind of very right side of the periodic table. We call those guys the noble gases. They turn out to be very stable, which is why we call them noble. They're like the royalty of the periodic table. Okay, so we take the noble gas that we end at before we make it to the new row that we're in. We put that in brackets, and then we don't have to write the electron configuration up to that point. It's like we're saying, okay, yeah, all the electron configuration up to this element at the end of the row is there. I'm just not going to write it. The only thing I write is what comes after that. Okay. Your column 18 stuff is also the column for P6. So a lot of times you can kind of pick out where you've got a kind of noble gas sitting there, kind of a checkpoint at the end of a row by looking for a P6 in your electron configuration. So if I'm looking at my iron up here, okay, and I don't have a periodic table handy, I could probably give a good guess that this 3p6 right here is the end of one of the rows. And it turns out it is. If I go and find what ends in 3p6, that's argon. So everything before 3p6, and including 3p6, this is the electron configuration for argon. And rather than writing that whole thing out, I could put argon in brackets like this, these little square brackets, okay? And that indicates this is argon's electron configuration, okay? So all I would have to write is argon in brackets, and then whatever comes after that, in this case 4s2, 3d6. And that saves me a whole bunch of time, and it saves me a whole bunch of space, especially if I'm starting from scratch and I know I'm going to be able to leave some of that stuff out. So let's look at something that's going to have a very long electron configuration, something like strontium. Strontium, let's see, is in the 1, 2, 3, 4, 5, fifth row down, okay, and it's in the S block. So it's going to end in the 5th energy level. It's in the 2nd column, which means it's going to end in S2 of the S block. So I'm going to leave myself a little note over here. It's going to end in 5S2. All right. So again, I could go and write all the way up through the 1s2, 2s2, 2p6, 3s2, 3p6, and try and write all the stuff into it. But really, I don't need to. Instead, I can look at what ends the row before strontium and use that as kind of a checkpoint, a bookmark to say this is where I leave off. So if I back up before strontium, I get rubidium, and then before that, I get krypton, which is the end of a row, big old Kr. Kr is in column 18. It is one of those elements that ends in P6. Specifically, krypton ends in 1, 2, 3, 4, 4p6. So if I put Kr for krypton in brackets here, what that means is the electron configuration of all that stuff up through 4p6. So that would be like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. All that is included in this little Kr in brackets. Okay, now I'm kind of defeating the point of doing the shortcut because I just wrote all that out. But when you take advantage of the shortcut, it'll be like, hey, I don't have to write all this stuff out. I can just write Kr in brackets, and that's what I mean. I'm saying everything up through 4p6 is included in those brackets. Okay. From there, I just have to write what comes after 4p6 until I hit 5s2. Well, after 4p6, check my diagonal chart. There's my 4p6. Hey, 5s2 comes next. So all I literally have to do, Kr, krypton includes everything up through 4p6. So what comes next is 5s2, and then that's it. I'm done. So much easier, so much less space. Now, if we are doing an abbreviation like this for a noble gas, for something in column 18, it would be great if we could just say, oh, okay, what's the electron configuration of argon? Put argon in brackets, because that's all of argon's electron configuration, and then we stop there. And it does technically end a row, but we're writing an electron configuration for a reason, because we care about what those electrons are and where they're at. So this kind of defeats the point of showing the electron configuration at all. So if we are dealing with a noble gas, we can't just put that noble gas in brackets and say, oh, we'll call it a day there. Instead, we have to abbreviate it with the previous row's noble gas. So argon ends its row, right, and it ends at 3p6. So again, I'm going to leave myself a note. That's where I'm going to stop, 3p6. Okay, but I have to look at the noble gas in the row before it to see where I kind of leap off at. Okay, where I take off at would be, in this case, neon. Neon is the previous noble gas, that other column 18 element before it. So I can put neon in brackets, and E, bracket that up, and then continue on from there until I hit 3p6. Neon ends at 2p6. So I'm picking up after 2p6 to write the rest of this. Well, after 2p6 comes 3s2, and then 3p6, and then I'm done. Okay, so I don't have to write out the 1s2, 2s2, 2p6 for neon. It's all included right here. So that gives us kind of the basis of how to write electron configurations and how to make it a little less awful as we're doing it.